And so I'll show you a few things about triangles and how it works, and then the meshing. So I already talked a bit about the numerical scheme, so maybe I should have talked about that before, but why we use triangles and how we do it. But that's basically this. And you can find more details in Aaron Roland's PhD thesis, and there's also some proceedings from a workshop at CNWF. We have a paper, it's not in press, not published, and some other stuff we did for the causal reflection. So basically, the reason why you may want to use triangles is that you may want to have high resolution in some place and coarse in another one. You can always do that with nesting, and that was the idea of Hendrik with the multigrid. But it can be sometimes difficult to really have the different resolutions going all the way from coarse to fine. So for example, if you do this kind of estuary, you're going in from here to there, you may want to nest with this one, that one, and it really gets crazy. That's one reason. Another reason you may want to use triangles is to actually minimize as much as possible the number of nodes by adapting the resolution to the wave field gradient. And this is one extreme case here. There was a paper we did some time ago using only 900 nodes, so it's a very small grid instead of nodes. Yesterday, the one we ran was 12,000, to give you an idea. But I was running that with exact node interactions, which are 300 times slower than the DIA calculation. So you can afford the exact calculations on this kind of small grid because it has very few nodes. Another nice thing with triangles is you get a better orientation of the shoreline, and that's nice if you want to do coastal reflection, for example. And of course, yeah, so you have other alternatives, curvilinear grids, quad trees, or the SMC grid within WaveWatch. Some other people use hexagons, and it's all a matter of taste and how you find it easy. And I don't know how to help you with the other ones, so I'll basically go to the most simple thing, which is a triangle. And so I briefly showed that also before. So essentially, the grid is organized in nodes. So node number 1, 2, 3, 4, and so forth. Then you have some triangles. And each node belongs to several triangles, and the numerical schemes for updating the energy at the nodes is based on this median dual cell principle. So if you take the center of the triangle and you join the half of the segments, you get this pattern, and this is how you define the edges of the cell to compute the fluxes going in the nodes. So you just have to provide WaveWatch with the nodes and the list of triangles, how they set up. There's one small special thing we do also to help with the boundary condition, is to also list as elements the points which are on the boundary. So in order to do that, we use the Gmesh format. So the Gmesh is another tool for meshing, for making these mesh. I actually have never used Gmesh, I just use the format which goes into that program. So we have different types of elements. And so type 15 for the elements are points, and we use that to define the boundary points. And type 2 elements are triangles. And so the mesh is just one list of nodes and then a list of elements, starting with the boundary point elements. There is nothing else. We haven't kept the neighboring, the connectivity of the grid. So how one node is connected to its neighbor is actually recomputed when you run W3 grid, so it takes a bit of time. So you have a grid with 1 million nodes. The W3 grid can take some time because it's searching for all the neighbors, and we may not have used the best algorithm for that. So if you have better alternatives, we'll be happy to update the code with something else. Right now, the grid I've been using here was mostly up to 300,000 nodes or something like that. I know Aaron has been working with something bigger, but he was doing like Hurricane Sandy with 3 million nodes and things like this. But yeah, if I go to that point, maybe I'll have to do something a bit more different in the WaveWatch code. In terms of the code, essentially we keep the same structure of the grid. So the triangular grid looks like any other grid, except that it has we use like the number of points in X is now the number of points in total, and we just set the number of points in Y direction to be equal to 1. So we have it's like a huge long vector, and with that logic, you can actually use the ASCII output or the NetCDF output, and you'll get the output on that grid. It will just be formatted as this very long vector. In the netcdf, we'll actually store also the triangle information, so you can actually plot everything from just one single netcdf file, which if you're making one netcdf file for every time step and every field, it's going to be big because each netcdf file will have in the header a variable which specifies the triangle. So you may actually want to have, netcdf files for at least, several time steps and several variables to save some space. And so right now we're just using that mesh format. It would be very easy to have options to do something else. So if you have some needs for that, we could actually build that in WaveWatch. But the version we have now is only capable of reading this Gmesh format. The other option is to, outside of WaveWatch, to transform your mesh into this Gmesh format. And we actually did that in the previous schools. People had some meshes for AdCirc and some other grids. So we had some programs for doing this. And so there's basically nothing has changed compared to what we were using yesterday. Actually, yesterday we already ran a mesh with triangle meshes, and so if you specify the grid type, it has to be it says it's a unst grid for unstructured. Would have been better call it tree something, but it's called unst. T here is because for longitude and latitude, and there's no wrapping around, so there's none. And actually, for triangular grids, you wouldn't need to do something special for wrapping around. So you can just, if you have some triangles that contain points at different latitude and longitude going all around the Earth, that should be able to run the global grid with triangles. I haven't tried it, but there's no reason why it shouldn't work. And then you just need to define these different depths. So the first depth, again, is a limiting bottom depth, which discriminates between points that will be always land and points that can be sea. Okay, so and then you have the minimum water depth, which at each time step will actually define what is land and what is sea as a function of the water level. And then there's a scale factor and all that stuff. So usually I in my mesh, I have depths that are positive down. And so to make it in the full WaveWatch convention, I have the scale factor here, which is equal to -1. And then you just specify that you'll read a file name with this whatever name. So here's an example with a Hawaii grid. So there's nothing else to change. You don't need to change the switches. The same code that will run with triangles. So the only tricky part is the active input boundary points, because typically, except for Philippe, who's going to run the Étang de Berre, it doesn't have any active points, don't have to worry about it. But you have a piece of ocean and you do it in coastal area, you have to worry about where are the boundary points. There's two ways to do it. You can either give the list of the points in the grid.inp file, or you can tell WaveWatch to detect them automatically with some threshold on the depth. And so this, this is not correct anymore. So it's in the name list, it's not UG, now it's UNST. Yeah, it's written here. In future versions, we are already in the future. It's been replaced by UNST, and with name list, it will actually detect, it will actually tell WaveWatch that all the points that are on the boundary and that have a depth larger than 20 meters will be considered as open boundary points. And so that's one way to make your life easier. Otherwise, you have to find the list of points, and we have, I think that Polymesh, the gridding program, will do some output for you if you want, but sometimes it's not possible to have a simple threshold for the depths to define the output points. Like if you're working on in the North Sea or in the shallow water area, where you have some boundary that crosses shallow water, you still won't have some boundary in shallow water, so you have to be careful. The time integration for the unstructured grids. So we also working with these 4 time steps. Okay, so we have the global time step, the advection time step, and the other ones. But the advection time step may not be the time step which is actually used. If you're using the explicit schemes, then this time step will be dynamically adjusted for each frequency to make sure the model doesn't blow up. And so if you tell it 120 seconds and you have a very small triangle somewhere in your grid, in order to make sure that it doesn't blow up, maybe WaveWatch will use something which is as small as 0.1 second. And so you run WaveWatch and it's nothing's happening. It just seems that it's hanging on, but it's actually just computing all these small time steps all these sub steps. So here there will be like a 1,000 or more time step before that. So how to make it faster? Or first of all, how do you know about it? So first thing to do is, okay, you can output the CFL numbers. So in the output variables, there's a CFL output for the spatial advection. So that's one way, but it's not easy because, well, you have to wait until the first output time step to get some results. And what we actually do, and what I will show you to do, is if you actually compile the Root shell with a T switch. So in the switch, you can have some test outputs, and you put that in, and then it will actually put out to the screen into a separate file the list of all the points which are requiring the smaller time steps. And typically, these are the nodes that you may want to move around in your grid to make the time step bigger. The other option is to run with an implicit scheme. And so the choice between explicit and implicit is done with a name list. And it's with a UNST name list, and it's explained in a manual. So I will show you that this afternoon, or maybe it's just after. Okay, so I don't like these implicit schemes too much because, okay, you can run with big time step, but what is the error? So you don't have much control over it. So I prefer to have a mesh which is optimized to run with explicit schemes. And so there's 3 options to do that. Yeah, okay, so yeah, the option 1 was, okay, go use implicit schemes, cross your fingers. I hope that the result will be okay. Option 2, if you actually have many nodes with a small time step, you probably have to update your meshing criteria and redo the mesh. And what's happening, and especially with Polymesh, is that a lot of the resolution is dictated by the shoreline resolution. So what Polymesh will do, it will make triangles along the shore that are at least as small as the spacing of your shoreline polygon. So you can request some coarsening on the shoreline, and I will show you how to do that. And that may be one thing we have to do. Another option is to make a smaller domain. So you wanted to have the full French coast with resolution of 100 meter, but you're really only interested in a small bay. So okay, we'll just get rid of everything else. I only do that small bay. And if you only have a few points that are causing problems, which are requesting this very small time step, what can be done is, so typically, you wanted to have something like 15-second time step, but there's 200 nodes that are calling for a time step of 3 seconds or smaller. What you can do is actually to use what we call a mesh doctor to clean up the mesh, move the nodes around, maybe remove a few of them. And I will show you how to do that with our IDL tools. We just load the mesh in IDL, and then we have some tools to clean up the mesh and update it. Okay, so I already talked about that. So the 4 schemes we have are these. So there's the one actually we use here quite a lot is a narrow stencil scheme. It's more diffusive, and it's less accurate, but it's cheaper. And to give you an idea, with a model with wave interactions and the source and everything, if the cost of that model is 15, and you want to go from the N scheme to the PSI scheme, so here it's going to increase the cost of the model a bit. If you actually go to the higher order scheme, the explicit FCT scheme, which is very little diffusion, then the cost of the model can be much higher. In that case, the propagation scheme takes a lot of time. The other option is the 4th option is to use the implicit scheme. So it's called, in WaveWatch, the name list is IMP. So IMP is for implicit. And actually, there's twice. I think we changed that to IMPS N. That was kind of weird. Well, I have to check what the thing is. I think it's a manual. And yeah, and the high order schemes are more expensive and they have less numerical diffusion. And the choice of scheme is made by the name list UNST, not UG, because we're in the future. So this is some examples of an example with waves and an island. So you send waves from the left to the right. This is an island. And this is the shadow behind the island with the N scheme, the PSI scheme, and the FCT scheme. And of course, you would expect to have more shadow and less diffusion in that case. This is how it looks like if you put some shoreline. So for the Mediterranean, like Greece and Crete here. So again, the N scheme, the PSI scheme, the FCT scheme. Of course, the wave field is never like that, especially in the Mediterranean. You don't have a swell with super narrow directional spreading. So as soon as you put some directional spreading, the difference between the scheme is not that big. And so we looked at that for realistic cases. That was a master thesis of Romain Canquet in 2008, comparing the N scheme, the PSI scheme in WaveWatch for California. So this is Los Angeles, is around here. You have the Channel Islands, and there's buoys, CDIP buoys here and there. And you can see here that in the N scheme here, you have more diffuse things, and here's a kind of narrow energy band. And actually, the result from that model was more accurate compared to the buoy. So sometimes diffusion of the numerical scheme is representing some real diffusion effect, maybe diffraction or something, which is not explicitly in the model. So maybe sometimes diffusion is good, right? And so actually, we use that N scheme most of the time. And so some other results are, so actually this is using the same mesh, I think we used yesterday, looking at the buoy 62069, which is offshore of here. So here you have the observation in black, and the model results without any current in red, and then with the currents with the other symbols, showing you the result of the model in the coastal area. So that works pretty well. And that's in another place, close to Saint-Malo in the English Channel. So that's the height of the wind sea, and you have some interaction of the wind sea with the current. So here again, you have this modulation of the wave with the current, and there is some shift, and I think it's more due to the breaking parameterization than the numerics that we have some errors here. And we've also been using in Hawaii with some coastal reflection. So there are some comparisons. Okay, yeah, that was a mesh. And we're looking at a buoy here, which is just 6 or 7 nodes from the coastline. And this is big, no, this is, yeah, Honolulu is here. And so it's this island here inside of the mesh, and you see the triangles here. And that's the result of that, for example. So you have the wave heights observed in blue, the model in red with 10% reflection on the shoreline, and the other one with a slope. So we define the reflection from the slope, we get the green line here. So the reflection has no impact on the wave height. It has some impact on directional spreading. And so here you see the model without any reflection gives you directional spreading in dashed line and the observations in blue. And with some proper reflection on the shoreline, we get the green line, which I think is a pretty good results. And yeah, that's it. So that's triangles. So we've been working with these triangles for almost 6 years now. And it's been included in Prévimère for, yeah, it's more than that now. It's been 3 or 4 years. So we had the Signcast of 20 years. There was the Omer project. And as I said, there's 4 different schemes to choose from, and we prefer here to use the N scheme. Aaron Roland, I think in general, uses the PSI scheme because it's a good trade-off between coast and diffusion. And if you may want to run with the implicit scheme. I don't know. Personally, I try to avoid it just because we don't control the error so well. And then what I will show you is how to actually make this mesh. And I'll just go with that now. So I'm not sure we have to cut. Yeah, you want to cut it? Okay. So any questions about triangles?